Okay, so I just wanted to talk a little bit more about Abel's theorem before we get into some examples. And so just as a reminder, what is Abel's theorem? If we have two solutions to our second order linear homogeneous differential equation, then we could write the Wronskian in this weird way, c e to the integral p of t dt. So that means that the Wronskian for us will always be 0 or never 0, but the important key here is that that is true on the interval on which the solution exists. So why is that important? Is because could the Wronskian of y1 and y2 at t be equal to something like just t? Notice that t is sometimes 0 and sometimes not 0. But this Abel's theorem says that the Wronskian is either always 0 or never 0. So could our Wronskian be t? Yes, it could. Yes. As long as t equals 0 is not included in the interval on which the solution exists. Okay. So do you remember how that could happen? For example, if p of t was like a 1 over t, right? That would mean that you want to throw out that t equals 0. Okay. So there is a little bit of a subtlety here on the interval on which the solution exists, and we'll talk about that more as we go. There's some exercises that that you'll look at that'll help explain that. Okay, so there's a really cool application of the Wronskian that I wanted to talk about. And so suppose that I have a differential equation of the form t squared y double prime minus, I'm going to be careful, t times t plus 2 times y prime plus t plus 2 times y equals 0. So part A, find the Wronskian for any two solutions to our differential equation using Abel's theorem. Okay, so notice that this is not the right form, right? I have to divide by t squared before I do that. And so I'll take y double prime minus t times t plus 2 over t squared, y prime plus t plus 2 over t squared times y equals 0. Good. Now I can cancel one of those t's out. And this is your p of t now with the negative sign. And so by Abel's theorem, the Wronskian between two solutions is c e to the minus integral, but the minuses are going to cancel. Integral of t plus 2 over t dt. Good. And so let's go ahead. Can you read that? I can rewrite that. Let's just put this off to the side here. T plus 2 over t dt is equal to the integral of 1 plus 2 over t dt. So that's going to be t plus 2 times the natural log of t, right? And so when I exponentiate that, I'm going to have e to the t plus 2 times the natural log of t, right? So that's going to be e to the t times e to the 2 natural log of t. The 2 comes out around the top, right? So that's going to be e to the t times e to the natural log of t squared, which is t squared. So we end up with t squared e to the t. Okay, did everybody follow the algebra there? You can rewind it if you'd like to. Ct squared e to the t. Good. And so you'll notice, right, that our Wronskian here, we have to stay away from t equals 0. And of course we have to anyway, right? Good. Okay, B. Now, I know the Wronskian has to be c times t squared e to the t for some c. If I pick different y1 and y2, right, that just means I get a different c, right? That's why the c is there, right? So if I pick different functions, I get a different c. Okay, so suppose y1, suppose that I know y1, and I know y1 to be what function? Te to the t. And I'm going to leave that as an exercise for you to show that y1 actually solves the differential equation. It's not hard, but you can see here, right, that you're going to have to use the product rule a couple of times, right? So the algebra gets a little messy, but that's okay. Okay, can we find y2? Well, notice a really interesting point. I now have two different ways of computing the Wronskian. Two ways of computing the Wronskian. Method one is by using Abel, right? And I know from that my Wronskian is c t squared e to the t. Now the second method is using the definition and using this function. And so in that case, the Wronskian is going to be the determinant of t e to the t with an unknown y2, right? Then the derivative of that's going to be e to the t plus t e to the t. The derivative of that's going to be y2 prime. And so I'll be left with t e to the t y2 prime minus e to the t plus t. We're going to get rid of these exponentials here in just a second. y2. Good. Are you ready? Because now these two things have to be equal to each other. And if you set these two things equal to each other, what do you get? Do you see that you get a differential equation in y2? So put 1 and 2 together, and we get that t e to the t y2 prime. We'll simplify this in just a second. Minus e to the t plus t e to the t y2 is equal to c t squared e to the t. Okay, where c is again yet to be determined. All right. If we get rid of the e to the t's, things cancel a lot. Okay, so then we have t. Am I getting down to the bottom of the page here? Can you still see? T y2 prime minus 1 plus t times y2 is equal to ct squared. What kind of a differential equation is that? It is first order linear in y2. And we know how to solve all first order linear differential equations. Well, just about all. So let's go ahead and pause for a second to the next page. I'm going to rewrite this. I'm going to pause this so you don't have to watch me. Okay, let's see if we can finish this up. So we're going to divide both sides by, or divide everything by t to get this in standard form. So y2 prime minus 1 plus t over t times y2 is equal to c times t, right? And now my integrating factor is going to be e to the minus integral 1 plus t over t dt. And notice that that's going to be 1 plus t is going to be 1 over t plus t, right? dt, so that's going to be the natural log of t. Oops, plus 1, sorry. Got ahead of myself, plus t. Good. And so that's going to be a negative sign in there. So e to the minus natural log of t and times e to the minus t, what is that going to be? That's going to be 1 over t to the t. And so now we have, geez, my chair's just squeaky, squeaky. T e to the t prime is equal to ct divided by t e to the t. So that's just going to be c e to the minus t, right? Good. So now if I integrate both sides, I'm going to get, what am I going to get? Minus oh, we'll go ahead and keep the c there. E to the minus c plus c2, right? And so y2 is going to be multiply everything by t e to the t minus c. Let's see, if I multiply this by e to the t, I'm going to have just a t plus c2 t e to the t. Good. Now there's our general solution, right? So what are we seeing in this? This part right here, you might have seen that t e to the t is already taken up in y1. So if I want my two functions to be completely separate from each other, then I can just take y2 of t to be just equal to t. Okay, and so just to double check that, let's go ahead and take the Wronskian. So that's going to be t e to the t was y1, and then y2 we said was t, and let's see if that's going to agree with what we said the Wronskian was before. So that's t e to the t minus t e to the t minus t squared e to the t equals minus t squared e to the t. Do you remember what we said before? See if I can find it. What did we say the Wronskian was for y1 and y2? Right here. This is where we started. Let me see if I can remember it right here. Here's where we started. So for this particular y2, y1 and y2, right, we ended up with c being equal to minus 1. This c being minus 1. Good. And so this is a really nice trick, right? So what I just showed is that if I know one solution to the homogeneous differential equation, I can find the second solution by computing the Wronskian in two ways. And in doing so, we end up with a first order linear differential equation in our unknown function. Good. And so that's a nice little trick. And there's going to be some review problems that will help you kind of do these computations for yourself. All right. I'll see you in the next video.